Okay, good afternoon, everyone. In the beginning of the class, let us see the new announcements. Okay, the first new announcement is March 8th, 2022 videos uploaded. Hi everyone, I have uploaded today's is here. Today's means March 8th, 2022. Today's class videos to YouTube. The URLs are this one, and this one. Best regards, Wei Zhen. Okay, the second announcement is the handout of chapter 1 has been updated. Hi everyone, I have uploaded the newest version of the handout of chapter 1 to equals2 website. The location and the file name are equals2 website, wireless communications and machine learning, course content, handouts, chapter 1, handout 20220310.pdf. Compared with the previous version, the update in this version includes 1. Page 22, problem 2, answer line 1, change authors to authors. 2. Page 22, problem 3, answer, change it is left to you as an exercise to please see the blackboard. 3. Page 22, add the problem, what is accrued and its answer. 4. Page 22, problem 8, add the answer to this problem. Best regards, Wei Zhen. Okay, next let us see the progress of the previous class. Okay, in the previous class we have taught to chapter 1, slides, page 20, handout, problem 1, answer. Okay, it is unfinished. Okay, please open your handout and turn to the page 20. Okay, and problem 1. What is the classic multi-armed bandit MAB problem? Okay, answer. In probability theory and machine learning, the multi-armed bandit problem, sometimes called the K or N-armed bandit problem, is a problem in which a fixed limited set of resources must be allocated between competing alternative choices in a way that maximizes their expected gain, when each choice's properties are only partially known at the time of allocation and may become better understood as time passes or by allocating resources to the choice. This is a classic reinforcement learning problem. Okay, we will explain what is the reinforcement learning in problem 2. Okay, problem that exemplifies. Okay, this is give an example. Okay, to explain something. The exploitation trade-off dilemma. Okay, what is this dilemma? Okay, we will introduce this dilemma in problem 3. The name comes from imagining a gambler at a row of slot machines, sometimes known as one-armed bandits. See figure 7. Okay, please see figure 7. Okay, this is figure 7. A row of slot machines in Las Vegas. Okay, what is slot machine? Okay, let me show you a figure. Okay, the first one. Okay, this is a figure of the slot machine. Okay, you can see that there is a bar here, and you put down this bar, and there are 3 wheels here, and they will rotate again and again. Okay, when they stop, if you see 777 in the middle, then congratulations, you win a big prize. Okay, in the Chinese, the slot machine is called the 老虎机, okay, or 吃饺子老虎. Okay, let us go back to the handout. Okay, who has to decide which machines to play? Okay, how many times to play each machine, and in which order to play them, and whether to continue with the current machine or try a different machine. The multi-armed bandit problem also falls into the broad category of stochastic scheduling. Okay, the second problem, what is reinforcement learning? Okay, answer. Reinforcement learning, RL, is an area of machine learning concerned with how intelligent agents ought to take actions in an environment in order to maximize the notion of cumulative reward. And the third problem, what is the exploration-exploitation trade-off dilemma? Okay, answer. The exploration-exploitation trade-off is a dilemma we frequently face in choosing between options. Should you choose what you know and get something close to what you expect? This is the exploit. Or choose something you aren't sure about and possibly learn more, explore. Okay, this happens all the time in everyday life. Okay, favorite restaurant or the new one, current job or hunt around, normal route home or try another, and many more. You sacrifice one to have the other. It's a trade-off. Which of these you should choose depends on how costly the information about the consequences is to gain, how long you will be able to take advantage of it, and how large the benefit to you is. Okay, to know more about the exploration-exploitation trade-off dilemma, please see reference 45. Okay, reference 45. What is the explore-exploit trade-off? Okay, next let us see what is stochastic scheduling. Answer. Stochastic scheduling concerns scheduling. Okay, we will explain what is scheduling in problem 5. Okay, problems involving random attributes such as random processing times, random due dates, random weights, and stochastic machine breakdowns. Okay. Then what is scheduling? Okay, it is an important concept in the wireless communications and networks. Answer: a schedule or a timetable as a basic time management tool consists of a list of times at which possible tasks, events, or actions are intended to take place, or of a sequence of events in the chronological order. Okay, that is in the time order in which such things are intended to take place. Okay, for example, the Google Calendar. Okay, let us go to the Google Calendar. Okay, for example, it is my schedule. Okay, and now it's time to teach the course Wireless Communications and Machine Learning from 4:15 to 5:30 p.m. Okay, and yesterday I will teach the course Special Topics on Cooperative Communications group meeting from 9:10 a.m. to 12 o'clock p.m. Okay, so Google Calendar is a kind of scheduling. Okay, so in the wireless communications or networks, okay, what is scheduling? Okay, it is that the system decide which time to serve which user and for how long. Okay, like this. Okay, this is the scheduling. Okay, problem 6. What is a restless multi-armed bandit RMAB problem? Okay, answer. In a generalization called the restless bandit problem, the states of non-plate arms can also evolve over time. Okay. Then let us go back to the slides. Okay, we are talking about the restless multi-armed bandit RMAB problem, which is a generalization of the classic multi-armed bandit MAB problem. Okay, what does the arm mean? Okay, arms. Okay, please go back to the picture here. Okay, we have told you there is a bar in the right hand side of this slot machine. So this bar is also called an arm. Okay, ARM, arm. Okay, back to the slides. Okay, you can see Gittins in 1979. Okay, Gittins in 1979. Okay, it is a paper published in Journal of the Royal Statistical Society in 1979. And Lai and Robbins in 1985. Okay, Lai and Robbins in 1985. Published in Advances in Applied Mathematics. Okay, and Natharam et al. In 1987. Okay, and Natharam et al. Okay, which is a paper published in IEEE Transactions on Automatic Control in 1987. Okay, in the classic MAB problem, the states of passive arms remain frozen. Okay, what is passive arms? That is the arm which is not pulled by you. Okay, it is static or unchanged. Okay, so it remains frozen. which is not suitable to model cognitive radio networks, where the channel states used for transmission or not change dynamically. Okay, so we use the classic MAB problem. Let the arm to represent the channel. Okay, so arm has only two states. Okay, what is the two state? Okay, it's you can pull down the arm or left the arm unchanged here. So you have two states. So similarly, each channel has two states used for transmission or not. Okay, because the channel will change even if you do not use the channel. So it is not suitable to use the classic map problem to model the cognitive radio networks channels. In contrast, in the RMAB setting, the state of each arm, active or passive, can change. Okay, thus the class of RMAB problems considered here has been studied in recent years in the context of cognitive radio networks in Taking and Liu in 2012. Okay, Taking and Liu in 2012, which is a paper published in IEEE Transactions on Information Theory. So you can know that this course is related to another course titled Information Theory, okay, which is a graduate course in our department and is offered by Professor Mao Ching Chu. Okay, and Liu et al. In 2013. Okay, we can see that Liu et al. In 2013. It is also a paper published in IEEE Transactions on Information Theory. And Gaffney and Cohen in 2018 B and A. Okay, Gaffney and Cohen in 2018 B. Okay. This is a conference paper in Proceedings of the IEEE International Symposium on Information Theories, ISIT. Okay, it is a famous conference in the field of information theory. And Gaffney and Cohen in 2018 A, which is submitted to IEEE Transactions on Automatic Control. But as to my best knowledge, this paper is already published. Okay, let us copy the title of the paper and use the Google search. Okay, here, this paper is published in IEEE Transactions on Automatic Control in 2021. Okay, the RMAB problem under the Bayesian formulation with non-Markovian dynamics has been shown to be p-space hard in general. Okay, what is p-space hard? Okay, let us see the handouts. Okay, handout, page 21, the first problem. What is p-space hard? Okay, answer. We say a problem is p-space hard if any problem in p-space can be reduced to it. Okay, then what is the p-space? Okay, problem 2. What is p-space? Okay, answer. In computational complexity theory, P-space is the set of all decision problems that can be solved by a Turing machine using a polynomial amount of space. The third problem, what is computational complexity theory? Answer. Computational complexity theory focuses on classifying computational problems according to their resource usage and relating these classes to each other. Okay, then what is a computational problem? Okay, answer. In theoretical computer science, a computational problem is a problem that a computer might be able to solve, or a question that a computer may be able to answer. For example, the problem of factoring. Given a positive integer n, find a non-trivial prime factor of n is a computational problem. Okay, for example, now I give you a positive integer 6, and I ask you to find a non-trivial prime factor of 6. So you can compute and answer me. The answer is 2 or 3. So this is a computational problem. Okay, then what is a decision problem? Answer. In computability theory and computational complexity theory, a decision problem is a problem that can be posed as a yes-no question of the input values. An example of a decision problem is deciding whether a given natural number is prime. Okay. For example, I ask you, is 1 is prime? Is 1 a prime number? Okay, your answer should be no. Okay, for another example, if I ask you, is 55 a prime number? Okay, your answer should be no, because 55 is equal to 5 times 11. Okay, next, what is a Turing machine? Answer. A Turing machine is a mathematical model of computation that defines an abstract machine that manipulates symbols on a strip of tape according to a table of rules. And finally, what is the amount of space? Answer. The space complexity of an algorithm or a computer program is the amount of memory space required to solve an instance of the computational problem as a function of characteristics of the input. Okay, let us go back to the slides. So we have explained what is P-space hard. Okay, please see the reference Papadimitriou and Tsiklis in 1999. Okay, this paper, okay, which is published in Mathematics of Operations Research. Okay, nevertheless, that is, however, there are a number of studies that obtained optimal solutions for some special cases of RMAB models. Oh, sorry. Okay, next page. Okay, in particular, the myopic. Okay, what is the myopic? Okay, let us see the handout. Page 22. Okay, it is 25 minutes. Let us take a break.